Hello everyone, welcome to Physics CQ-METANS. This is the fourth video lecture on vector analysis. These are the topics I will be discussing in this video. I'll be starting with the application of scalar and the vector product, which we have recently studied, and then I will start with this triple product. So in triple product I will be discussing triple scalar and triple vector product. Application of vector product. Before we move on to the application, let us recapitulate. So we have studied the scalar and the vector product. So we know that the scalar product, if I have two vectors a and b, so the scalar product or the dot product is represented as a dot b, and mathematically it is ab, the cos angle between them, cos of the angle between a and b, or we can, or this a dot b is just multiplication of the components of a and b. So it is ax bx plus ay py plus az bz, and the cross product is a cross b, which is equal to a vector. So we know that the cross product of two vectors give us a vector. So this c is a vector whose magnitude is ab sine theta, and the direction of this vector c or a cross b is perpendicular to the plane of a and b. So if this is a, this is my vector b. So if we see, this makes an plane. So any vector perpendicular to this is the vector c, or the direction can be also be determined by using the right-handed screw rule. Now let us see the application of the scalar or the dot product. The simplest example is the work done. Now we know that the work done is written as force times displacement. But now how do we get this? So let us understand vectorially. Now suppose if the force and displacement are not in the same direction. So this is the displacement and this is the force. So now this force and displacement are at some angle theta. Now what we have to do is we will resolve the components. What we will resolve the component of this force. So there will be an component along this, there will be a component of force along the displacement. We will call that component as F parallel, and there will be a component of force perpendicular to the displacement vector. We will call it as F perpendicular. So that is what is also mentioned over here. So if force and displacement are not parallel, so if force and displacement are not parallel, then we have to resolve the force into the components. So there are two components. One is parallel, that is the component of force parallel to displacement. We are calling it as F parallel, and the perpendicular one is the component of force perpendicular to displacement, that we are representing as F perpendicular. Now we know that dot product is A dot B is equal to AB cosine of theta. This is the definition of dot product. We will use this. Now see the component of force which is perpendicular to displacement. So this is the displacement vector, and this is the component of force which is perpendicular to displacement. So the angle between them is 90. So if I put over here, so we find that this obtains the result as 0. So the component, the perpendicular component of the force does not do any work, so does no work. So the work done is by the component of force that is parallel to displacement. So we have W is equal to F parallel dot D. So this is the dot product of F parallel times D. So but what is F parallel? From this we know that this F parallel is F cosine of theta. So we get F cos theta times D. Now from this we can write it as F d cos theta, purposefully written because if we see there is one magnitude of one vector, magnitude of another vector, the angle between them, the cosine angle between them gives us A dot B. So this we can write it as F dot D. So this is how we'll end up with the work done formula. Now this was fine. This I have a displacement in direction, in some direction, force in some direction, but now what if we have some complicated trajectory? Say this is some trajectory performed by some particle. Now if we notice the displacement vector changes every time. So how to deal with this? So even if we see the angle between the force and this displacement vector changes, so obviously then there will be, so it is not easy as this problem to calculate the work done. So if the force varies with distance and direction of motion, d changes with time. So then what we do is we take an infinitesimal element from this curve and call it as dr. Now why we take this infinitesimal length element? So if we have this curve and if I take only this small part and if I zoom this small part, I will find that in this part this looks like a straight line. And if I find out the work done for this, so I find out the work done for this, I take another small part, I find out the work done for this, I take small part, find the work done for this part, find the work done for this, and add them all. I will get the work done for this entire line. But there is a nicer way, we will see how it is. So then we write for an infinitesimal vector displacement dr. So dr is the small length element along that path. So for this displacement dr, we write work done. Now for that small length element, work done I am representing as dw. So that is f dot dr. Now if we integrate this integral dw, that is equal to integral f dot dr, we will get the work done. With the proper limits or given initial conditions, we can solve this integral. Now, but the thing is, we haven't yet dealt with the line integrals. So we will come up how to integrate this when we will study the line integrals. So we will study how to integrate this dw in the line integrals topic. Next is the application of cross product. The simplest example is torque. Now for a seesaw, let us draw one seesaw over here. So this is a seesaw and this is the point of pivotment which we called it as fulcrum. This is O. This is the force which is acting downward, and let us call this force as some F prime. These are vectors. So for seesaw we have a quantity called torque or momentum is the rotational effect. So we know that torque is a turning effect, gives a turning effect of a force. So tau is represented as Ft. It is not a vectorial notation, just written. So where d, now what is this d? F, we know it is force, but what is this d? D is the distance from the fulcrum O, this capital O, from the fulcrum to the line of action of force. What it means is, so this is fulcrum. So from the fulcrum to the line of action of F. So the line of action of F is this. So this distance is d. And from here, if I say, let us call this distance as d prime, because here the force is F prime. Now this d has a name. It is called as the lever arm. So it is the lever arm of F. Lever arm by definition is perpendicular distance from O to the line of action of F. So it is a perpendicular distance. So perpendicular distance means, so okay, fine. So O, this is my O. So it is a perpendicular distance from where to where? The line of action, the line of action of force. This is the line of action of force. So it should be perpendicular to it. So this distance, this is what we have represented as d. But this is the actual definition of lever arm. So the torque of a force about O is defined. So how we can deal now? See, this is my R vector. See, this is some vector F over here. That this is force and this is the radial vector. So if we extend this over here like this is the angle theta, and if we extend this, so this look, this should look right, and this one. So if this angle is theta, this should be theta, because opposite angles are equal. So this component is r sine theta. So F into r sine theta. So lever arm, so as the definition is, tau is equal to, so here the definition is perpendicular distance. So which is the perpendicular distance? So if this is r sine theta, so F is perpendicular to it. So if we take this F and plot it back, so it meets over here. So this is the perpendicular distance from the line of action of force. So we can write F r sine theta. If you don't like this, we can resolve force. So if I resolve force, so there will be two components. One will be over here like this. Sorry, it should be like this. So this is not looking good. So I will draw with different pen. So this is how this force will be. So this force will be F perpendicular, and with the which is in the line of R, we will call it as F parallel. So again, F perpendicular, this is nothing but F sine of theta, and this is F cosine of theta. So now again, this is R and this is the line of action of force. So that is F sine theta and times R. So we get, anyhow we do, we get the same thing. So this is F R sine theta. Now let me remind you, A cross B vector can be written as modulus of A modulus of B into sine of theta. So here also we have some F component of force times R into the sine angle between them. This looks somewhat similar to this. So I can write this F R sine theta as the cross product, that is R cross F. So this is the formula for torque. This is how we'll land up with the formula of torque. The magnitude. Now the magnitude is this. And direction, again the direction is same as P2 for the cross product, like perpendicular to the plane of R cross F. So if we complete this, like if we draw this and complete this, so this represents an plane. So the perpendicular to that will be the torque. Or else we can always use the right hand screw rule. Now again I want to emphasize that lever arm, it is the perpendicular distance from the point of pivotment to the line of action of force. Next we move on to the triple product. Now triple, as the name suggests, triple. So it is something of three quantities. So triple quantity, triple product means I will have, now we are dealing with vectors. So I will have three vectors, A, B and vector C. Now there is a product. So I should either have dot or cross product and it will give me some result. Now if I have three vectors and I perform some operation on it, and if the result I get it as scalar, so I will call that as scalar, a triple scalar product. And if the result is vector, then it is triple vector product, just as we did in the dot and the cross product. Dot product is what? The result is scalar, so it is a scalar dot product. So let us see. So scalar triple product, so which gives the result as a scalar. So we perform some operation, so that operation is A dot B cross C. So scalar product, if I do some operation on these three vectors, so the result will give me a scalar. And triple product, which gives the result as a vector, so which is A cross B cross C. It is written as this. Let us see what the scalar triple product is, or sorry, it should read as triple scalar product. Now this triple scalar product, it is also written as A dot B cross C, which we have seen just a few seconds back. Now there is a useful geometrical interpretation of triple scalar product. This is very important, very crucial, because this will give you some idea what this is. Now what we do is we construct a parallelepiped. It's parallelepiped with the vectors A, B and C. Let us do that. So let us take some vector, like let us say this vector is B, this vector is C and this vector is A. Let's say the angle between B and C is theta and this angle is phi, and we are using the general coordinates. This is x, this is y and this one is z. Now this face will represent the base area. This is the base area, and this is nothing but equal to the product, that is B cross C. If I multiply B and C, so I will get this. So this is what we get. So now the height, because we know that we should have length, breadth and height to find out the volume of a cuboid or this parallelepiped. So the base area is B cross C. So B cross C, we know we can write it as B modulus of B modulus of C sine of theta. Now the height of parallelepiped. So in order to find out the height, let us take this. Now this is vector A. What is the projection of this vector A on this axis? This is y axis. So the projection of vector A can be obtained by dropping a perpendicular on the y-axis. So what this will be? This will be modulus of A into cosine of phi. Now if I just displace this vector, so this green color, if I just consider this like some pencil or something is kept over here, and I just displace this and bring this vector over here and drop it. So this vector will represent the height of this parallelepiped. So the height of the parallelepiped is a cos modulus of a cos phi. So the volume, now how can we find out the volume? Base area into the height, or else length into breadth into height if it is a cuboid. So volume can be written as base area. Base area is modulus of b, modulus of vector c, sine theta times the height. This is the height. This is height and this is area. This one is the area. So a cos phi. Now I know that b c sine theta. So this is same as we dealt over here, that it is a b sine theta is a cross b. So I can just write it as this b cross c. So that is what we have written over here. Now this is b modulus of b modulus of c sine theta. We write it for the modulus of b cross c. Now there is a cos theta. So this modulus b cross c modulus a cos phi. Now b cross c is a vector. We know that this b cross c is some vector. If you want to call, let's say b cross c is some vector d. So we know that a dot b is equal to modulus of a modulus of vector b into cosine of angle between them. So is it looks similar to this. So b cross c, we have, let us call it as d. So modulus of d modulus of a into cos phi. So it will give me a dot d. But what is d? D is b cross c. So we get it as a dot b cross c. Now if this phi is greater than 90, then the result will turn out to be negative. We'll see how it is. So now what this a dot b cross c physically means? Geometric interpretation, it gives the volume of the parallelepiped. So a dot b cross c represents the volume. So this is what we have. Now rather than this b, if I call this vector as something different, let's take another thing. Let us call this as a. Let us call this vector as a. And this vector to be c only, and this vector to be b. So just consider what we have dealt over there. So a is the base, c is the width, and b is not the height, b is that vector. We have to find out the height b. So it will be b cos phi. So if we do so, then in this notation, my a cross c will give me the area, and b cos phi is going to give us the height of the parallelepiped. So I will get a cross c, that is nothing but the area times b cos phi, which is nothing but b dot a cross c. So I get this. So this is also the volume of the same parallelepiped, only the vectors are different. So can I say that, so this equal to what we have done, a dot b cross c, a dot b cross c. All these are vectors. All these are vectors. Keep in mind. So I have a dot b cross c, then I have b dot c cross a, it should be, but according to our notations, this is what. Then c dot a cross b. This is what we have. That's fine. So this 3 should be equal. So this equals to this and this equal to this. So this will give me the volume, and all this 3 will be equal. Now, if we change the ordering, like in the bracket I have A cross C. If I write C cross A, then there will be a negative sign, because we know that the cross product is non-commutative. Sorry, this is what we write. So if there is a change in ordering, then there will be a negative sign. This is important. So there are 6 such triple scalar product. So these are 3. So if I change the ordering, there will be a negative sign. So if I accept, so if I neglect that negative sign, so we have such 6 scalar triple product. So all are equal except for the sign. So this will give me a volume. This is also going to give us a volume. This also is going to give us a volume. So if I interchange them, so if I write B dot C cross A, that will also give us a volume, but with a negative sign. A dot C cross B also will give me the volume, but with a negative sign. So we get 6 triple scalar product all equal except for the sign, or 13 if you count both. A dot, now dot products are commutative. So if I write A dot B cross C or B cross C dot A, it is one and the same. So if we do so, we get 13 such types. So I would suggest you, so just try to find out these 13 types. Just write them and check whether we get 13 or not. And if you don't get 13, just mention in the comment section. I will just write them for you. So now to write the triple product in component form, we first write this B cross C. Now how we write this B cross C? Remember, so this is B cross C, that is equal to the determinant I, J, K. Then here we have the component Bx, By, Bz and Cx, Cy, Cz. So this is how the determinant we write, which is mentioned over here. So B cross C is this. Now we dot with A. So whatever this is, we dot with A. So I will just write this component, what this B cross Cx represents. So I cap, what we do is we neglect this row and column and we multiply this two. So we get I cap By Cz minus Bz Cy. So this component we are calling it as B cross C this component we call it as B cross C X component because it is in the ith. So A dot B cross C is Ax, B cross C X component, Ay, B cross C Y component, Az, B cross C Z component. Now we can write it in a very nice way. So A dot B cross C can be written as Ax, Ay, Az. In the determinant Ax, Ay, Az, Bx, By, Bz and Cx, Cy, Cz. So if you solve this, you will get this equation only. So just let us try doing this. So this should be multiplied by Ax if I solve this. So if I solve the determinant, we solve this determinant. So only the x component. So it will be Ax times this By times Cz minus this Bz times Cy. So we get this same expression. So similarly, if you complete this, you will get all these things. So this is just an algebra done over here. You can just go through this. So we have written C dot A cross B, so which can be also written as A dot B cross C. So if we do so by changing the So that 13 expressions which are coming, so if we just interchange, we can get this. That is what it means. The last thing is triple scalar product is written as in the bracket parenthesis ABC. So if I write in the bracket A, vector B, vector C, it represents A dot B cross C, the triple product, scalar triple product, the vector, triple vector product. Now, as mentioned, it is written as A cross B cross C. The result will give me a vector. Now, here actually it is modulus of B cross C. So, modulus of B cross C is perpendicular to the plane of B and C. So, this is nothing but the direction of the vector product. So, A cross B cross C is perpendicular to the plane of A and B cross C. So, here we have mentioned figure. So, in figure, any vector perpendicular to B cross C. So, let us see. Let us draw this. So, this is my vector B, and see this is the vector C. So, the perpendicular to this is the vector B cross C. So, any vector perpendicular to B cross C lies in the perpendicular to B cross C, that is in the plane of B and C. So, if I have any vector, so if this is B cross C, so if I have any vector A along this, so this, the cross product A cross B cross C will be in the plane of B and C, in this plane only. That is what this statement means. And we can write this as a linear combination. This is more important. So we can write it in the linear combination of A times vector B plus B times vector C, where A and B are scalars which we are interested to find out. We will come to this, what this is. This is very crucial. This A and B, the scalars which we are going to find are very important, because this is going to give us an identity. Now, one way to find out this A and B is to write out this A cross B cross C in component form. Let us take one example. So let B is equal to B x I cap, C vector is equal to Cx I cap plus Cy j cap, and vector A is Ax I cap, Ay j cap, and Az k cap. So this is the addition of this three. Then vector B cross C. So B cross C. Vector B is this Bx I cap and C is this. Now this multiplied by the first term. So B I cross I is 0, 1. This multiplied with this bx cy I cross j, I cross j, bx cy I cross j, I cross j is nothing but k. So we get this b cross c as bx cy k cap. Now we have to cross this with a. So a cross b cross c. So a vector is this. So that shouldn't be this a. So a vector is this. So it is ax I cap plus ay j cap. So this vector A is Ax I cap plus Ay j cap plus Az k cap. And what is this B cross C? B cross C is this Bx Cy k cap. Now Ax, so this multiplied with this. So I get Ax Bx Cy I cross k. I cross k is minus j. So I get this first term. Then this multiplied by this. So Ay Bx Cy j cross k is I. So we get Ay Bx Cy and j cross k is I, and k cross k is 0. So we're not writing that. Now let us see that all these things mention some expression. So let us see. Now this Ax and Bx I have over here. So can I write it as Ax Bx is equal to A dot B, considering that the product Ay By and Az Bz is 0. I can write it in this way. Ax Bx is equal to A dot B. Now I have something over here. I also have this AY and CY. So if I write AY, CY as A dot C, that is also fine. Then this vector C is right from here. Cx I cap plus Cy j cap, and vector B already we have, that is Bx I cap. This vectors we have. Now let us see this. So let me write this vector again over here. This is Ax, Bx, Cy, and minus j cap plus Ay, Cy, Bx I cap. Now this Ax, Bx, we can write it as A dot B. This is vector, obviously. Cy, this is in bracket I will write, and Cy j cap is nothing but C, the vector C, plus, and there is a minus sign, so I bring this minus sign as it is over here. This is the first term. Now the next term, A by Cy, I can write it as A dotted with C, and Bx I cap is nothing but B. So we get an identity, A dot C times B minus A dot B times C. This is an identity. So using all this equation, I can get A cross B cross C is equal to A dot C times B minus A dot B times C. Sometimes dealing with the dot product is more easy than dealing with this. We write in this form. Now if you refer Merrill-Bose, so it says that this formula is very important and it should be learned. It should be learned but not memorized. So now they are telling us how to learn this formula. So in the Merrill-Bose only, it is taken from Merrill-Bose. The value of triple product is product of linear combination. Product of linear combination of the two vectors in the parenthesis. So it is the linear combination of these two vectors B and C. So means what? This B can be written in some like something, some scalar times this vector B and some scalar times this vector C. This is what it means. So it is a linear combination of the two vectors in the parenthesis, that is B cross C, B and C, the coefficient of each vector. So this, if you notice, then this before B, so it is A dot C. What is A dot C? A dot C is a vector. The dot product, scalar dot product, the result is a scalar. So A dot C is a scalar. So this is a scalar. A dot B. A dot B is also a scalar. So this is some scalar times a vector and scalar times some vector. So this is a linear combination. So what we was mentioning over here, so if we compare that results, so A becomes A dot C and this B becomes minus A dot B. So this is what we get. The coefficient of each vector is dot product of other two. That's right. So the coefficient. So B has a coefficient. So if B is a vector, so the remaining two, we should take the dot product. So we have it. It says that. So C, if I am taking a vector, the remaining two should give me the dot product. The middle vector in the triple product, the middle vector, now over here it is B, will always have a positive sign. Now see, in this equation you will never find that this B has a negative sign. If it has, so then something will change. Now we move on to the application, the last part. Now in Cartesian coordinate system, the volume element of a rectangular box is dx dy dz. So let us see what it says. Say this is my coordinate system. This is x, y, and z. Now say this is some rectangular box in this coordinate system. So now let us write this as dy, this is dx, and this is dz. Rather, I should have said that we will take a small infinitesimal volume element of length dx, dy, and dz. But let us consider that this volume itself is very small, and the lengths of this is dx, dy, and dz respectively. Now let us define another coordinate system, CUVW. Now the volume element may be approximately a parallelepiped. We don't know. Let us say. Suppose we are given the formulas of x, y, z as function of new variables. So x is a function of, sorry, u x is a function of UVW. Then y also is a function of UVW, and z is also a function of U, V, and W. So then we want what we want to find out is this volume element in terms of this UVW. Now let us say that we have this coordinate system UVW. This is U, V, and W. So there is a vector in the direction of, in the increasing direction of A, while B and W remains constant. So if I define dr as we have done earlier, the length element in the Cartesian coordinates. So this is dr in the Cartesian coordinates. Now in the Cartesian coordinates, it can there can be an dr. This is dr in the Cartesian coordinate system. So that is I cap dx plus j cap dy plus k cap dz. Then how can I write this vector? So vector A is differentiation of this with respect to du, because u and v are constant. So if I differentiate, I get dx by du, because see, this x is a function of u, v, and w. So dy by du and dz by du times du. This is one equation. Similarly, if I take along v and w the vector p and c respectively with the increasing v and w, we get something. So similarly, if b vector b is along the increasing vh while keeping u and w constant of the volume element, and c is along the increasing w while keeping u and v constant, so we get this equation. So b will be dr by dv, because b is in the increasing vh. So we can write this. So dr by dv is I dx by dv, dy by dv, and d. So we know this. Similarly, c can be written in this way. Now how can we write a dot b cross c? A dot b cross c can be written in this determinant form, right? So the this is the x components. So this is ax, ay, az. See, ax is dx by du, ay is dy by du, and az is dz by du, and that's what we have written. Similarly, this represents the p vector, and this represents the component of c vector. This should be, sorry, extremely sorry, this should be du, dv, and dw. So now this determinant is nicely written as J. So it can be written as J du dv dw, where this J is called as the Jacobian. This determinant is very important when we solve the problems in thermodynamics. In thermodynamics, this will oftenly come up. Oftenly, we have to use this Jacobian. So this Jacobian, we have written what this Jacobian determinant is. We will solve this. We will solve one problem on Jacobian shortly. So at that time, we will try to explain how important this Jacobian is in terms of thermodynamics. So that's it for this one. So thank you all. Thank you all for joining me. So see you in the next video. Thanks a lot.